Okay. Let's see here. Okay, let's go. All right. Okay. All right. So, thanks everyone for coming to watch this video. My name is Raymond Fan, and I'm a PhD candidate in my 4th year with the Department of Electrical and Computer Engineering here at Ryerson University. And the topic of discussion today is an advanced MATLAB tutorial for engineers and scientists focused on the upper year students. This is an advanced tutorial that will teach you cool tools that you can use for your thesis work or for any courses that require MATLAB to use. And I'm assuming that you have basic knowledge in MATLAB, the inner workings of how it works, just creating basic variables or whatever. But if you don't have that knowledge, we'll cover that in brief detail. But I will cover what you need to know. And the reason why I'm doing this video tutorial is I did have this talk on Monday, February 6th, but I didn't opt for a video record because there weren't that as many people as I would hope. So just to ensure fairness for the people who actually did come out, I just decided to talk to them, and I didn't put a video up. But due to popular demand, a lot of people have been asking me to post a video tutorial, and I guess I can't. I don't know. I guess I'll succumb to public opinion. So here is the video that has been popularly requested. So this is just a personal video tutorial that I will be doing on my own. I'm just in my lab right now, and I'm doing this tutorial for the benefit of you. So the tutorial is going to be decomposed into 2 parts. The first part is just a quick intro to what MATLAB is and where you can get it, and then we'll go through a brief review, or I think it's brief, of the underlying workings of the inner workings of MATLAB. So basic operations, how to create arrays, how to create matrices. The 2 main methods of operation in MATLAB are using matrix algebra and using point-by-point operations. So the distinguishing features have not been properly taught in most of the courses that I've TA'd in the past. So hopefully this will serve as a means of distinguishing between the 2, so you're able to understand them better. And we'll take a look at how to modify and extract a portion of a matrix, where instead of in C style, where you write a couple of for loops to access elements one at a time, you're able to extract a portion of a matrix using just a single line of code, and it's a lot more powerful in this environment. And then we'll take a look at how to create and how to work with dynamic arrays. You have arrays which are of an unknown size. So what you do is you just set them to be a blank array, and then you can populate the elements as you go, and the size of the array will dynamically increase depending on what stuff you put in the array. And then we'll get on to creating what's called a function handler, which are basically ways of creating equations of single or multiple variables. For those who have taken BME or ELE 532, the inline crap is very ancient. I don't like the way that it's taught. It's not as flexible as function handlers. So hopefully at the end of this tutorial you'll be able to do the same stuff that you did for 532, but with the use of function handlers, and it's the more proper way of coding functions for you to plot stuff. So the next part we're going to talk about is how to plot graphs properly. So the trend in terms of plotting graphs is non-standardized depending on the course that you take a look at. Personally, I don't like the way that the way for plotting graphs is taught. They assume that you have absolutely no idea. If you're seeing MATLAB for the first time, what some courses will do is that they just give you a whole bunch of code and say, here, mess with it. So it's like not knowing how to swim, and they toss you in a pool and saying learn how to swim. It's kind of like that kind of analogy, where they just give you a whole bunch of code, you just type it all in, and then you take a look, and then you just observe. So hopefully this part of the tutorial will teach you how to properly plot graphs using function handlers, so you're able to create the best looking graphs and that you know what you're doing. And I'll show you how to plot multiple separate graphs in the same window, and then how to use MATLAB syntax to customize the plots, how to add a legend, how to label the axes, how to make a title of the graph. And then I'll throw in a little bit of a bonus, how to show a 3D plots, surface and mesh plots. I'll make that as a little bit of a bonus towards the end. And then we'll take a look at some useful MATLAB commands and constructs. So for example, I'm going to remove the structures part because it's a little too advanced, so we're just going to cover cell arrays. Okay, so we're going to just take a look at how to create cell arrays, how to, a review of logical operators, and or not. And the find command is really useful too because it'll allow you to locate certain locations of an array or a matrix that meet certain criteria. So if you want, you can use the find command that will say find all the numbers that are greater than 2 and less than 4, and then it'll give you the locations of where these values are in a matrix or an array. And then you can modify matrices using logical operators. So it's pretty much related to the find command. So we'll go through that later. And then this is akin to those who are taking ELE 639, creating transfer functions, both polynomial form and zero-pole gain format. The transfer functions are a backbone to any differential equation course that you take or a control system course that you take. So it'll be cool if you can use MATLAB to help you do that analysis. And we'll take a look at minimum realizations, which I'll talk about later. How to calculate the impulse and step response. Those are the two main things that you see in a lot of signal analysis courses in the Department of Electrical and Computer Engineering. And finding the roots of equations is a very useful thing too, where most conventional calculators that you buy, scientific calculators that range between $15 and $30, can only find roots of up to a polynomial equation of the third order. Any equations that you have that are greater than the third order, you can't find the roots using just conventional calculators. So MATLAB is a tool that you can use to find any roots up to the power of order n, which is great. So you're not restricted to to the order of the system. You can just specify whatever polynomial you want. And also we're able to find roots of nonlinear equations. Nonlinear equations are those like sine or cos or exponential. MATLAB employs root finding techniques such as bisection method or Newton's method to be able to find the roots of those nonlinear equations for you, and I'll show you how to do that in MATLAB syntax. And then it's very important. Another thing that's important is to evaluate a polynomial equation. So if you have an equation like x squared plus 3x plus 5, how to use MATLAB to give you what the output is if you were to substitute different points into the equation. And then partial fraction decomposition is a really cool tool where if you wanted to take a polynomial equation that is decomposed into a fraction, you can represent it as a sum of smaller fractions. And you've seen that in any differential equations course or Calculus 2 for engineers in particular. And then last but not least, we're going to cover just a couple of cool commands that will help you create matrices, create a matrix by taking a copy of a smaller, just taking a smaller matrix and copying it left to right, top to bottom, and how to convert an array and reshape it as a 2D matrix. So a single column vector and to reshape it as a 2D matrix. And then the second part of this tutorial, we're going to take a look at some advanced math analysis. So if you are familiar with the Wolfram online integrator, you type in an equation and then you submit it and then it gives you what the integral is. You can achieve the same thing if you do it in MATLAB, if you do it properly. We're going to calculate the analytical equations, the closed form equations of derivatives and integrals using what's called the symbolic mathematics toolbox that's in MATLAB. Essentially, you use MATLAB to calculate what the derivative or integral is with respect to a variable x or whatever variable you want. And then you can evaluate the derivatives at points. You can calculate the definite integral. We're going to show you how to do that. And then the next thing that's really cool that's not taught in our program is how to find the line of best fit via regression. The students in our program, they don't take numerical analysis, which I think is a really useful course, especially for the stuff that we do. You find the line of best fit by regression. So this is more commonly known as polynomial interpolation. So I'm going to show you how to use MATLAB, where if you have a whole bunch of points where you don't know which function it came from, this will help you find the best line of fit that connects all of them as best as possible through regression or through polynomial interpolation. That's what it's normally known as. And then we can use MATLAB to calculate the area under a curve. When you just have a set of points and you don't know what the function is, you can calculate it by what's known as the trapezoidal rule, where you take pairs of neighboring points and then you calculate the area under a trapezoid. And then all you have to do is just add up all these areas together, and that's the area under the curve. So it's kind of like Riemann sums, but instead of using rectangles, you use trapezoids. And then last but not least, we're going to go through how to solve differential equations on a numerical basis. There's a lot of different ways to solve differential equations, but I'm going to show you the most simplest way, which is using matrix algebra. So how differential equations work in this context is that when you do it on paper, or when you're writing it out, you come up with a closed form solution. You come up with a function of x or time or so. When you do it in a numerical solution, what happens here is that the output is not an actual equation, but it's a set of points where each point tells you what the true or what the estimated value of that solution to the differential equation is at that point in time. And then just to tip of the hat to the computer scientists, how to sort arrays. Okay, so let's go through the introduction. So MATLAB stands for Matrix Laboratory. It's a portmanteau of two names, matrix and laboratory. It was created by a guy named Cleve Moeller at Stanford University in 1970. And the reason why he created this environment is because a lot of the tools that were available to do a lot of linear algebra stuff and a lot of numerical analysis stuff were not suitable, or they were not good enough for the applications that he wanted to make. So he created another environment that would allow him to do this stuff a lot quicker, a lot faster, and so that's the whole purpose of MATLAB. It's to make things like linear algebra, numerical analysis, and optimization a lot easier to do. MATLAB is a really cool thing because it's what is known as a dynamically typed programming language, which means that you don't have to declare any variables like in C programming. Before you use any variable, you got to declare it first. You also got to declare the type of variable that it is. With MATLAB, all you got to do is just specify what the name of the variable that you want, and then you just you just populate it with whatever you want, and then what will happen is that it will create just enough memory for you that will store the stuff that you want in that variable, and it gives you that variable of the name that you want. MATLAB treats all variables as matrices. So, for example, a scalar is considered a 1-by-1 matrix. A vector is a 1-by-n or an n-by-1 matrix. And the reason why we consider variables in terms of matrices is that the backbone of how MATLAB operates is to use matrices. And it makes calculations a lot faster, as you'll see later. So where can you get MATLAB, or how can I use MATLAB? Well, there's three ways. The first way is if you're a student in our program of the electrical and computer engineering department. So if you're a biomedical engineering student or electrical or comp, you just basically use any of the computers that are on the 3rd and 4th floor of the engineering building. You log on to your account using the information that was given to you in 2nd year. So if you're a first-year student of these programs, the first option will not work for you. You have to wait till your 2nd year, which is unfortunate. But if you do have access to an account, just log in, go to Applications, go to Math, and then go to MATLAB R2010B. So the Applications menu is on the top left corner, and then just follow the Math tab, and then go ahead and click on MATLAB 2010B to start it. If you're not in our program, but you would like to use MATLAB on any of the other computers that are connected to the Matrix network, so for example, if you're in the library or if you are in Kerr Hall West 71, all you got to do is just log in onto a computer that's connected to the network using your Blackboard password and ID. So whatever ID you use to log into your Matrix email account, or Blackboard, you use the same thing here. Then simply you just go to Start Programs and just choose MATLAB R2011 and you're set. And last but not least, the best option that I consider is good is to install it on your own laptop or computer, because inevitably you will be using MATLAB later on in your upper year courses, and it's probably a good idea to install it now so that you don't there aren't any problems when you get to the later courses. So if you want to install MATLAB on your own computer, our department has a university-wide license that for all students enrolled at Ryerson to be able to use. Just go to www.ryerson.ca/MATLAB, and all you got to do is just follow the instructions on this website to be able to get MATLAB. The first thing that you have to do is you have to sign up for a MathWorks account, and to do that you have to be sure that you're on a computer that's connected to the Ryerson network. So if you want to be connected to the Ryerson network on your laptop, just simply connect to the wireless and then go and sign up for an account. Or if you want to sign up on any of the computers that are connected to the network, by all means do so. The reason why you have to be at Ryerson or be on the Ryerson network to sign up for an account is to be sure that MathWorks, the guys who created MATLAB, they want to double check to see whether or not you are a Ryerson student and you are eligible to use MATLAB for academic use. So they check the IP of the computer that you're at, just to double check to see if you are in fact a Ryerson student. Once you sign up for an account and once you associate your login with a MathWorks account, then you're able to download MATLAB wherever you want. You can download it on your laptop at home, your computer at home, wherever you want. You just have to be sure that you establish a MathWorks account at the Ryerson, on the Ryerson network first before you decide to download it. Okay, so a few things before we start. This is an advanced tutorial that I've talked about, so as I just said, so I assume that you have some basic knowledge in MATLAB. I will cover some concepts that you see in second year math courses. So for those who are in first year, you will see some stuff that you might not have seen before, so I will try to cover those as best as I can. Also, if there's a lot of things that you've forgotten, if there's a lot of basic MATLAB stuff that you've forgotten, don't worry, I'll cover those briefly, or I'll try to cover them as best as I can. And then also, if you don't have any exposure to MATLAB, that's totally fine. As long as you have some programming experience, you'll be able to understand the basics parts, so that we'll be able to get to understanding the more advanced concepts we'll be covering here. Assume that for each MATLAB line that I show you here, type it into the command prompt and push enter. So for every line that I show you, just immediately assume that I push enter after. You enter these commands in the MATLAB command prompt, so as soon as you open the window, you'll see double chevrons with a blinking cursor, and that's where you enter the commands into the MATLAB command prompt. Or you can open up a new a function script file, and you can throw the commands in there. You can copy and paste the commands in there, and then you can run the script file. So let's see here. So review of array and matrix operations. So how to create arrays. It's very, very simple. There's no need to allocate any memory whatsoever. All you got to do is just use a set of square braces. Well, you got to figure out the name of the variable that you want. So I'm going to call it the most original name possible that I can think of, which is array. You have an equal sign beside it, and then you have a pair of square braces. Inside the square braces are the numbers that you want to populate the array with for you to use. So as I talked about, if you want to create a single array, you can either make a row vector or a column vector. A row vector is what we're most used to. So all you have to do is just inside the square braces, you put in numbers, and then you separate each number by space. The spaces denote that you'll be moving over to each column. So in this case, I have a 4-element array with 1, 5, 8, and 7 that's separated by spaces. So 1, 5, 8, and 7. Oops, I got a mouse here. That's good. So 1, 5, 8, and 7. All right, and then here. And then all you got to do is separate it by space. If you want to create a column vector, all you got to do is you use a semicolon to go to the next row. So you'll do 1 semicolon 5. So this is the second row, third row, and then fourth row. This will skip over the columns, the spaces, and the semicolons will skip over to the rows. That's one way to create a column vector. The next way to create a column vector is to create a row vector and to simply transpose. What the transpose does is that it will interchange the rows in the column. So anything that became a row becomes a column. Anything that's in a column becomes a row. Okay? So you can create a row vector, and then when you use the transpose operator, which is a single apostrophe before the after you create the array or the vector or whatever, it'll transpose it for you, and then it makes it a 4x1 element vector. Okay? So once you populate the numbers that you want into the array, it will create just enough memory to store those numbers, and then it will store it into a variable called array. Very original. So to access elements in an array, it's very simple. All you got to do is just use the name of the array that the variable that you called. In this case, we'll call it array, and then you use round brackets right after the name of the variable that you created. And then inside the brackets, what you do is you specify the location of the number that you want to access. So the thing here is that MATLAB, this is mostly for computer scientists, is the fact that when you're accessing elements in C programming, you use index 0 to start with the first element. So for example, you do array and then a pair of square braces, and then 0 goes inside, which means that is the first element of the array that you want to access. In MATLAB, we use index 1 to start. So it's a common source of confusion amongst programming of trying to transfer between C and MATLAB. You start with an index of 1 and not 0. So that's one of the biggest things that you have to modify when you're transporting in between programs. So for example, if I create this array, it's 4 elements, 1, 5, 8, and 7, as we talked about before. If I want to access the second element, you do array and then bracket 2. What will happen is that it goes to the second element, checks what it is, number 5, and then it stores it into a variable called num. If I do it for the fourth location, 7, right, 1, 2, 3, 4, 7, and then it'll store the number 7 into a variable called num. Okay? You can also access a range of values. So for example, instead of accessing a single value, you can access a range of values. And what this will do is that it grabs a range of values that you want, and it creates a new array that will store those values into a new array for you. So for example, you have to use something which is called the colon operator, which is just a pair of dots in a vertical orientation. And how you do it is that you use the array, or the variable name that you called, and then you surround it with round braces, and then you use, first you have begin colon end. So what begin means is the location of where you want to start grabbing, and end is the location where you want to end grabbing. So for example, if I wanted to grab elements 2 to 4, you do array bracket 2 colon 4. And what that'll do is that'll create a new matrix, or new array for you, where the first element is 5, the second element is 8, and the third element is 7. And that's pretty much it. So here are some quick examples. For example, if I wanted to create an array where as I just talked about, if I wanted to grab elements 2 through 4, you do array 2 colon 4, it'll grab these 3 elements, put it into a new array called val, and then it'll give you a 3-element array such that the first element is the second element of the original one, which is 5, and then 8 and 7. If I wanted to create an array where I just wanted to grab the first 2 elements, in this case it's just 1 colon 2, right? So first element to the second element, it'll create a 2-element vector such that we'll have 1 and 5 to be stored in a new variable called val. Okay, and if we wanted to access elements in an out-of-order fashion, you can certainly do that by doing this. So what this means is that you have 2 braces, you have your round braces, and inside you have a pair of square braces. And then what you do is you specify the actual locations of what you want to access in a manual fashion. So what this is saying is that I want to create a 4-element array where the first element is the first element of the original one, which is 1. The second element I actually want to grab is the 4th index, which is 7. The next element I want to grab is the second one, which is 5. And the last one, 3, the third element, which is 8. So what you're doing is you're specifying elements to be in an out-of-order fashion, where it'll populate the array based on the locations that you manually specify. This is a good thing where if you want to grab certain elements in a array or matrix that satisfy a particular condition, and you're able to do that syntax, you're able to do that very nicely by doing this kind of thing. So another example would be, let's say I wanted to grab the first element and then the third element right after, and then the second element right after. So if we're using the this is pretty much the thing that we want to use, right? 1, 5, 8, 7. It says first you want to grab the first element, and then it's number 1, and then it asks you to grab the third element. So if you go to the third element, it's 8, and then the second element is 5, and that's what you get. Okay, pretty straightforward. Last thing about arrays is that if you want to copy an entire array over, all you got to do is just figure out another variable that you want. All right, just give it a name, and then what you do is you just copy it completely over by just using the equivalence operator or the assignment operator. So all you have to do is just, if I wanted to create a copy of the original matrix, call it array 2. If you just do array 2 equals array, it'll take every single element in array and copy it over to array 2, and that's what you get. Okay, not too bad. Okay, let's move on to matrices. Alright, so to create a matrix, it's very much like creating arrays. You use square braces, and then you just throw in all the numbers that you want inside the matrix. So you use spaces to separate between the columns, and use semicolons to go to each row. Very straightforward. So for example, if I wanted to create a 4x4 matrix, 1 through 4, 5 through 8, 9 to 12, and 13 to 16, all you got to do is do the following. So you have m equals, and then you have a left square brace. You fill in the numbers separated by space, so 1, 2, 3, 4, semicolon to go to the next row, 5, 6, 7, 8, semicolon to go to the next row, 9, 10, 11, 12, semicolon to go to the next row, 13, 14, 15, 16. Okay, so it's very simple to create matrices. All you got to do is just separate each column by space, separate each row by a semicolon. So how you access a particular element in a matrix is also very easy. You use the variable name, and then you follow it by a set of round braces. Okay, and then you use 2 numbers if you want to access a particular element. So the first number is the row that you want to access. You separate it by a comma, and then the second number is the column you want to access. So for example, if you wanted to access the second row and third column, right? So second row, third column, it's the number 7. You do 2, 3. And what this will do is that it accesses the second row, third column, it accesses number 7, and then it puts it into a new variable called b. Very simple. If I wanted to access the third row and the fourth column, you do 3, 4, and then it'll access the number 12, store that number into b, which is 12. Right? If I wanted to access the fourth row and the second column, it's very easy. All you got to do is just specify the fourth row, which is the first parameter, and the second row, which is the second column, which is the second parameter. So 4, 2, number 14, and it goes into B. If I wanted to access the first row and the third column, you do 1, 3, 1 for this is row number 1, column number 3, and you get the number 3. You store it into the variable B, and you're done. Very simple. Now, as with the arrays, we can access a range of values. So what we can do is, this is the part where we talk about extracting a portion of a matrix. So let's say I wanted to just grab a subset of the matrix. So what you do is you use the colon operator like what you've done before, but in this case you're going to use the colon operator on each dimension by itself. So for example, if I wanted to access rows 1 to 3 and columns 3 to 4, you do row, so you do the parameter, the matrix M, then you have your braces, and then you do 1, 3, which means access rows 1 to 3, and then you access columns 3 to 4. So 1 to 3, columns 3 to 4 is this. And what this will do is that it gives you a 3 by 2 matrix where you have 3, 4, 7, 8, and 11, 12. Very simple. All right. And then if you wanted to access a 2 by, you want to access rows 3 to 4 and columns 3 to 4, it'll be this matrix. You do 3, 4, and then 3, 4, and then you get this. Right? It's 11, 12, 15, 16. If I wanted to, you don't have to specify a colon operator for each dimension. If I just wanted to extract a single row, you do 1, so this is for the first row, and then columns 1 to 3. Right? And this is what you get. So columns 1 to 3. So you get a 3 element vector that's stored into B. If I wanted to grab the third and fourth rows and just the second column, right? This is what you get, 10 and 14. So you use the colon operator in each dimension to access the group of values that you want. So the last thing for accessing is if we just use the colon by itself. If you use the colon by itself for any dimensions, that means you want to access all the values for that particular dimension. So here's a quick example. If I wanted to grab rows 1 and 2 and all the columns, what this will do is that it gives you just the top half of this matrix, which is 1, 2, 3, 4, 5, 6, 7, 8. If I wanted to grab row 2 and get all the columns, it'll just give you this vector, which is 5, 6, 7, 8. If I wanted to grab all the rows and just column 3, it'll give you this, which is 3, 7, 11, 15. The semicolons mean you're going to the next column. And then finally, if I wanted to grab all the rows and the first 3 columns, so all the rows, first 3 columns, you get this. Actually, this is a mistake. Anyway, so you're grabbing all the rows, the first 3 columns, it would be this 4 by 3 matrix. So 1, 2, 3, 5, 6, 7, 9, 10, 11. So this is a mistake. I'm going to correct that, but you get that. Okay. Finally, as a little bit of a curveball, if I want to copy all the rows and all the columns, there's 2 ways you can do it. The first way is to specify a colon for each, dimension, which is technically correct, but it's a little superfluous. What you should do is do this one instead. What it'll do is that this is the assignment operators we talked about before for the arrays. What this will do is that it'll copy M to a completely new variable called A. It'll copy all the contents over to a new variable called A. So this is technically correct, but it's rarely used. We opt to use this one instead. So let's get on to some basic math operations, all right? So let's assume the following. Let's assume that A and B are vectors or arrays or matrices that are of compatible dimensions. And we assume that A and B can be properly added, subtracted, multiplied, divided. So what this means is that you have to be sure that A and B are of a compatible dimension where it shouldn't violate any laws when you add, subtract, or multiply and divide. So we're going to assume that they follow the right size guidelines for you to be able to do any of these operations. And we're also going to assume that n is a scalar number. Okay, so with all these assumptions, what we're going to do is here's a quick little table that provides a good summary of all the basic operations that you can perform on any vector, any array, or any matrix. And this is the following. So addition and subtraction we've seen, since childhood. So when you're dealing with addition and subtraction in terms of matrices, you got to be sure that they're both the same size, so the rows and columns are both the same. And when you add or subtract, what you're doing is you're adding or subtracting corresponding elements together to produce a new output that will reflect this. So for example, when you're adding or subtracting a matrix, it'll take the first element of A, you add it with the first element of B, and then the output in C, for example, would be the first element of C would be the first element of A with the first element of B added together, and the same can be said about subtracting. Right? For vectors, we pretty much do the same thing. Instead, you have to be sure that the vectors are the same length. You have to be sure that they're both row vectors or they're both column vectors. And when you add two vectors together, all you're doing is you're just adding each corresponding component together. So for example, if you had A is 1, 2, 3, and D is 4, 5, 6, when you add them, you'll get 5, 7, 9. All right, so you're adding the corresponding locations together. So here's an example. You know, I love examples. Examples are the best thing to show, you know, your point. I forgot to code these. So this would be C equals, you know, bracket 1, 2, 3, and then end bracket semicolon. The same thing for D. So I'm going to create these two matrices in MATLAB 1, 2, 3, 4, and 5, 6, 7, 8, right? 2 by 2. And then if I add these two things together, you're going to get 1 plus 5, which is 6, 2 plus 6, which is 8, 3 plus 7, 10, and then 4 plus 8, 12. Okay, if I were to subtract these two things, you're going to do 1 minus 5, it'll be minus 4, right? 2 minus 6, which is minus 4, and so on and so forth. So when you add, you're adding corresponding elements, it'll produce a new matrix with these, that reflects this. The same thing for when you subtract. If you're adding two vectors together, for example, if you were to do C plus D, you get 5, and then 2 plus 5 is 7, and then 3 plus 6 is 9. So you're adding the corresponding locations together to give you a new matrix that reflects the element by element addition. And then you can do the same thing for subtraction. If you were to subtract 1 minus 4, you get minus 3, 2 minus 5, you get minus 3, and 3 minus 6, you get minus 3. So it's very simple. So we're going to go back to this. Multiplication in this context, because we're assuming that A and B are matrices, or they're of compatible dimensions, this means matrix multiplication. Whereas when you do A times B, you're actually doing matrix multiplication. Division is a little more complicated. You have two different styles of division. The first, we have left division, and the next we have right division. So what left division means is that it takes the inverse of A and multiplies it by B. Right division means that it takes the inverse of B, and then you do A times that B inverse. So how you figure out which one is which, all you got to do is just take a look at the top of the slash and figure out where it's leaning towards. So the top of the slash here is leaning towards A, so left division means that you're going to take the inverse of A first, and then you're going to multiply by B. And then if you take a look this way, B is leaning, you know, this is leaning towards B, so you're going to do A times B inverse. So just take a look at the top of the slash and see where it's leaning towards. And then that will determine which inverse it takes. So the next one is simple. You know, this means the transpose. The single apostrophe means to take the transpose. We've seen this earlier. It just interchanges the rows and the columns. And then last but not least, you have exponentiation. What this means is that you're just going to multiply a matrix as many times as you want. That's specified by the number n. So if n was equal to 3, you'd multiply A 3 times, which is A times A times A. Okay, so some examples. So for example, I have A and B, which I've already coded from before. If you were to do A times B, what this will do is that it'll do a matrix multiplication for you. So this is 1 times 5, and then plus 7 times 2, which is 19. 1 times 6 plus 8 times 2, which is 22, so on and so forth. All right. A slash B here, this is the left division. What this does is that it finds the inverse of A, and then it multiplies it by B, and this is what you get. When you do A slash B, this is right division. It'll find the inverse of B, multiply by A, and then this is what you get. Okay. Now, if I were to do this operation, what this means is that you're going to multiply A twice. So you're going to do this, and then times this again, and this is what you get. Right? 7, 10, 15, 22. And then if you do B hat 3, this means that you're going to multiply B 3 times. So you do B times B, B times B, and then you get this. Very simple. Special case is if you want to add or subtract or multiply or divide a vector or a matrix by a single number, you can do that very easily. All you got to do is just specify the operation that you want, and then you just specify a constant number before or after, depending on what you want to do. So here's a quick example. I have a 2 by 2 matrix, which is 1, 2, 3, and 4. B is a 4-element vector, 5, 6, 7, 8. If I wanted to multiply every element by 2, you just do 2 times A, and then you get, 2, 4, 6, 8. If I wanted to divide every element in B by 3, you get a 4-element vector where this is 5 divided by 3, 6 divided by 3, 7 divided by 3, 8 divided by 3, and this is what you get. And then if I wanted to take every element in A and subtract it by 2, you'll get 1 minus 2, which is minus 1, 2 minus 2, which is 0, so on and so forth. So every single element in A is subtracted by 2. And then if I wanted to take every element in B and add it by 4, this is what you get. Okay, so it's very simple. So far we've done operations that only deal with matrix algebra. So there's another branch of operations that MATLAB heavily relies on, which is the really cool thing about MATLAB here. It's called point-by-point operations. What point-by-point operations are is, well, first they're only applied to 4 different operations. So you can only apply them to multiplication, left and right division, and exponentiation. So you can only apply dot operators to those 4 things only. To use point-by-point operators, what you do is you append a dot. You put a dot before the operation that you want. So, for example, if you want to do point-by-point for multiplication, you do dot star. If you wanted to do it for left or right division, you just put a dot before each of the slashes. And then you do the same thing for the exponentiation when you do dot hat. Okay? So point-by-point operators work in the following fashion. What you're going to do is if you were to do A dot star B, what it'll do is that it takes the first element of the matrix A, and then it'll multiply with the corresponding first element in B. And then the output of the matrix, which is C, the first element of C is just A, the first element of A multiplied by the first element of B, and that's the output, and that's it. You do the same thing for the division and for the this is a typo, there should be hat. So if you do it for exponentiation or division, it'll be exactly the same thing. You apply the operation only on corresponding pairs, and then the output reflects that operation on the corresponding pairs by themselves. So here's a quick example. If I wanted to create 2 matrices, as I just did before, A, 1, 2, 3, 4, B is 5, 6, 7, 8. Okay. If I wanted to do A times B, this is without the dot operator. This just performs your matrix multiplication as you did before. And then if I were to do A dot star B, what this means is that it'll take the first element of A multiplied with the first element of B. That's the output of D. Then it takes the second element of A multiplied by the second element of B. So 6 times 2, 12. So whatever position that both of them correspond to, the output will simply multiply those 2 corresponding positions together to get that output that you want. And then you have 3 times 7, which is 21. 4 times 8, which is 32. Okay? If I were to do A slash B, so you're going to take the inverse of A and then multiply by B, this is what you get. If I were to do A dot slash B, what this means is that it'll take every element of B and then divide by A. So 5 divided by 1 is 5. 6 divided by 2 is 3. 7 divided by 3 is 2.333, and so on and so forth. So this is the same thing as taking every corresponding element of B and dividing by its corresponding element in A. Okay? Oh, just pause here. I got something to deal with. Give me one moment. Okay, sorry. Let's see. Where was I? Okay. So, let's see. Where was I exactly? Okay. Yes. Okay, I finished that one. All right. So if we go to the next slide, what we're going to do is, if you were to perform a right division, it's very, very simple. You just take the inverse of B and then just multiply A and B together. Okay. And then when you do that, you produce this matrix, which is minus 3, minus 2, 2, minus 1. All right. Now, if you were to do a point-by-point operation, if you were to do a dot and then a slash, what this does is that it will take every element in B and then every element in A and then divide by B. So you're going to get 1 divided by 5, which is 0.2, 2 divided by 6, which is 0.333, and then 3 divided by 7, which is 0.4286, and then 4 divided by 8, which is 0.5. Okay, so this is the same thing as taking every element from A and dividing by its corresponding element in B. All right. If you were to do A hat 2, this is the same thing as just multiplying A twice, so then you get this. If you were to do A dot hat 2, this will become 1 squared, 2 squared, 3 squared, 4 squared. So what you're doing is you're taking every element in A and squaring it individually, and then you get an output J which reflects that. Okay. Now we're going to get onto modifying elements in arrays and matrices. All right. So we're pretty much going to do the same thing with accessing elements in groups. All you're going to do is you're just going to flip around the order of operations. So what you're doing is, for example, if you wanted to store the number 7 using the matrix A that we declared previously, if you want to store the number 7 in row 3, column 4, you do 3, 4, and then you get the number 7. All right. Similarly, if you wanted to group rows 1 and 2 and then columns 3 and 4 together, if you wanted to store the matrix 5, 6, 7, and 8 as a 2 by 2 matrix, you wanted to store it into rows 1 and 2, columns 3 and 4, you would simply take this matrix and you store it like that. Okay. And then similarly, if you wanted to replace row 2, all the columns with just a single row vector, okay, you would do the following. You do 8, 19, 2, and 20, and then that would simply take this row vector and override it with the second row of all the columns. Okay. Finally, if you wanted to take a column vector, right? If you wanted to take a column vector, do 5, 4, 3, and 2, and then you wanted to store it in the third column, you would simply do that. And then finally, if you wanted to take rows 1 and 2 and set all the columns to 5, that's what you would do. So the last thing for our review here for matrix and array operations is if you wanted to create a dynamic array. This is very good if you don't know what the size of the array is beforehand, and you simply create, you can create dynamic arrays that will grow in size depending on what stuff you add to it. You simply set a variable to an empty set of square braces, which is the following, and then all you got to do is you just populate the array with whatever you want. So this is good if you don't know the size of the array that you want. So for example, if you did this, and then if you were to do array and then 1, 4, what this will do is that it'll set locations 1 and 4 to the number 5. And then if I wanted to extend this, you do array and then 5, 7. What this will do is that it will add 8, 6, and 8 to the elements that are already there. So right now your array is going to be 5, 5, 5, 5. So 4 5s with 8, 6, and 8. Okay? And then you'll store this, and this is a 7-element array. And then last but not least, the end keyword is a pretty cool keyword to know. What this means in an array context is if you were to do array and then bracket and then end, what this will do is that it accesses the last element of the array. And if you want to extend this by putting a 7 just after the end, do an n+1. And what this will do is that the end keyword goes to the end of the array, and then when you add +1, it puts a 7 just right after the end and extends the size by 1 more. So all this syntax will give you 5, 5, 5, 5, 8, 6, 8, 7. Just the key thing to note is that when you create a dynamic array here, and if you were to remove this, if you were just to start populating right at index 5, what will happen is that the elements from 1 to 4 will become 0. So if you don't start at 1 right away, what it'll do is that it just pads whatever you did not fill in with zeros up until the point of where you start at. Very, very simple. So in this case, if you were to remove this statement, this becomes 0, 0, 0, 0, 8, 6, 8, 7. Okay, so that's done. So creating function handlers, we use MATLAB to create very complex equations. These equations, like what you see in an ELE 532 or BME 532, these equations will help us, plot things easier. Or what you do is you create a very complex equation, and then you put the variables or put the numbers to be substituted into the variables, and then you get an output that relates to those values that you put in. So these equations, these complex equations that we're going to be coding are what are known as function handlers. You can create single variable or multiple variable equations. Once you create your function handlers, all you got to do is just supply the function handler with the values that you want to substitute in as the variables, and then the output will be the output will be the function that is evaluated on the inputs that you supplied. All right. So it'll evaluate the function at those values and gives you outputs that relate to those functions. So to create function handlers, you use a very simple construct. You use the @ sign, and then after the @ sign, you have round braces that follow, and then inside the braces, you place the variables that are relevant to the equation that you want to code. So if you want to have an equation that has more than one variable, you separate each variable by a comma. Okay, so then once you do that, you write out the equation in C style. So a slash is divide, and a star is multiply, and so on and so forth. And a good thing to note is you have to make sure that all the multiplication, division, and exponentiation operations are point by point. The reason why is you want to use a function handler so that if you supply a matrix or if you supply a vector, what it'll do is that it will evaluate the function at each individual element by itself, and then it'll give you an output where the function was evaluated at every point in that array or matrix. Okay, so point by point will help you achieve that because you want to apply the operation only on corresponding elements. If you don't make it a point by point, what it'll do is that it will assume that you're trying to do a matrix division or matrix multiplication, whatever deals with matrices, and you will not get the right result. So a good example of built-in functions are like sine and cosine and square root. They take in a vector or they take in a matrix, and then the output is applying that function to every single element in that matrix by itself. Okay, so you don't need to do point by point if you're doing it with constants. So because the constants are a very special case, so when we're adding or subtracting by a constant number, or if we're multiplying by a constant number, you don't need to have a point by point operator in front of those numbers. So here are some function handler examples. For example, if I wanted to create a function which is 5 times sine x minus minus x squared plus 3, what you do is you create a function handler. You have the @ sign, and then you have a bracket x, right? And then you have 5 times sine x, okay, there's a constant there. And then you do minus x dot hat 2, right, which means that you're going to square, so you're doing an exponentiation, so you have to do point by point, and then you have plus 3. Okay, so you have the @ sign x, and then 5 times sine x minus x squared plus 3. So that's how you're coding the function handler. If you wanted to create a function with the square root, and then you have x cubed plus e to the power of minus 2x, exp means e to the power, and you have minus 5. You simply do @ and then the variable that's required for that function, which is x. Then you have square root, and then x dot hat 3, right? X cubed plus exponential minus 2x, 2 times, and then minus 5. If I wanted to create a function handler with 2 variables, you do @ and then inside you separate each variable by a comma. In this case, the function relies on x and y. So you do 25 minus x dot hat 2 minus y dot hat 2. This is a exponentiation operator. You have to be sure that's point by point. And then finally, we have what is known as Euler's equation, cos omega t plus I sine omega t. Right, it's a very popular equation that's used in signal analysis. We see that this function relies on 2 variables, omega, which is the frequency, and t. So if you wanted to create this function handler, you would do @ and then wt, and then cosine, and then because w and t are variables, make sure that you do a point-by-point operator, right, because we're multiplying. And then the same thing for sine. You got a point-by-point there, and then you multiply by I. So I is actually a supported character in MATLAB. It stands for the imaginary variable. So when you run this function, you will get a number with a real component and an imaginary component. So you can also nest function handlers within other ones. For example, if you had a function here, let's say it was 2x squared plus 3, and then you had another function which relied on the f function. So let's say this is g of x is 2x, and then f of x minus 3, and then plus 5x. So if you wanted to create a function handler that would, use a previous function handler, you would first create the one that you want, which is f, and then it only relies on the x variable, so @ and then bracket x, and then you have 2 times x dot hat 2, and then plus 3. All right, so you're creating that function handler, and then the next one, you have to be sure that you supply the function handler into this function handler because it requires f. So not only do you have the variable x, you also have to supply a function handler which is f. Okay, so you have 2 times and then x, and then because we're multiplying, this isn't a constant, so you got to do dot star and then plus 5 times x. So you're able to run through this stuff with nested function handlers, and you'll be able to get values. So this thing is superior to the inline because the inline operator won't allow you to nest inline statements, which is kind of messed up. Function handlers are a lot more better to use. Okay, so to use function handlers, you use them like any other function in MATLAB. So obviously it depends on how you name them, right? So you just, all you have to do is just name the, use the function handler, give it a name, and then you're gonna use that name, supply, numbers or matrices or vectors that you want the function handler to evaluate, and then it gives you an output that is the same size as what you specified as the input, applying that function to every single element of that array, in that vector or array or matrix on an individual basis. So here's a quick example. Let's say I wanted to create a 2 by 2 matrix, which is 1, 2, and then 3 and 4, right? 2 by 2 matrix. And then let's say we had a 3-element vector, which is 2.5, 6.7, and 9. All right. So you have a function, f of x, which is 5 sine x and then minus x squared plus 3. Okay. And then we have another function which is 25 minus x squared minus y squared. So we're going to create those two function handlers just like we seen the last time. Very, very simple. You've seen this before. And then what we're going to do is we're going to take the function handler, which is f, and we're going to substitute 3 into it. So if you were to do f of 3, this is equivalent to taking the number 3 and putting it inside this function. And then whatever number that you get is stored in a. So in MATLAB, the sinusoidal function is in radians, so this answer is with respect to radians. So you'll get minus 5.2944 where the sign's in radians. Similarly, if you wanted to use the function handler to apply it to a matrix, all you got to do is just specify the matrix, which is A in this case. And what this will do is that it will create a matrix that's of the same size, where the first element, you substitute 1 into the equation. The second element, you substitute 2 into the equation, and then 3, and then 4. So it gives you a matrix or a vector that is of the same size, where each element has the function evaluated for that particular point. And then last but not least, if you wanted to specify, G, this is our function handler for x and y. So we're assuming that B, these are our x values, so 2.5, 6.7, and 9. And then we're going to create a set of y values where you're just subtracting by 2. So this is 0.5, 4.7, and 7. You plug this in, and what will happen is that you're going to get 2.5 and 0.5 for x and y. You evaluate it in this function, you get an output. And then you're going to do 6.7 and 4.7. You plug this in. This is what that output is. And then 9 and 7, you put that here, and that's what you get. Okay? So next, we're going to deal with plotting graphs. I hope to be able to show you how to properly plot graphs, because the way that it's taught in most of the courses that I've TA'd is unacceptable. So I'm going to be hopefully this will be able to show you how to graph things properly in MATLAB, and we'll show you a little bit of a bonus on how to plot 3D things as well. So this is not properly taught in any of the courses that I've taught, as I talked about. And if you follow these 3 simple constructs, you should be able to create a very nice looking graph that's report worthy or thesis worthy. All right. So the basic run through are these 3 steps. First, you got to provide an array for each set of axes. So, for example, if you wanted to plot an x and if you wanted to graph a point, graph a 2D graph, you got to supply a pair of x points and a pair of y points. On a Cartesian grid. Okay. You plot an array of points for provide an array of points for each set of axes, each axis rather, and then you run a function that plots things for you. It's very simple. So you figure out what your x and y points are. You run a very simple command that'll plot stuff for you, and then you run a few more commands that will customize the graph for you. So add a grid, put a legend, axis, label the axes. So put an x, label the x-axis, label the y-axis, put a title on the graph, and so on and so forth. So let's start with 2D plotting. Assume that we have 2 variables, right, x and y, and they're both the same size, and they've got a whole bunch of points in each of the arrays. So to do the most basic graph, if you want to plot a graph of y versus x, all you got to do is just run the command plot x comma y, and then that's it. The exclamation marks are for showing you that it's that simple. Okay, and then it produces a nice looking graph. It's basic, but you can add a little more frill at the end. So let's start off with a very basic example: y is equal to x. So first, you need to generate a set of x and y values. So let's just do x is equal to 1, 2, 3, 4, 5, and so on, right? And then when you with y, we want y is equal to x. So you can either do 1, 2, 3, 4, 5, or you can just do y is equal to x. It's exactly the same thing. So when you have pairs of points, what this will do is that the default behavior is that it plots these points. So when x is equal to 1, y is equal to 1, x is 2, y is 2, 3, and so on and so forth. And then it does a connect the dots thing where it draws a straight line, it draws a line through all the points. It does a connect the dots kind of thing. And this is what you get. Okay? It's very basic graph. You can definitely improve this by adding a title, adding a grid line, and adding x and y axis, the titles and so on and so forth. But we'll get to that. We'll get to that in a little bit. So this is great. But what if we wanted to generate a large set of numbers? So instead of right now we only have a 5-element array, which is great. It's a small array that we can input all the numbers manually ourselves. But if you have a very large array that you want to plot, so for example, if you had a 2,000 element array or a 5,000 element array, you're not going to sit there and type in every single number individually from 1 up for the first number up to the 5,000th number. It's just not practical. So if the numbers follow a specific pattern, then it's actually very easy to create arrays that follow a particular pattern. And you use the following syntax. So for example, so you have array and then first, colon, increment, colon, last. And what this means is that you want to create an array that follows a pattern. So for example, if I wanted to create an array where we're starting from 1 and then you go to 20 in steps of 3, that is the syntax that we cover. So first is the value that you want to start at. So what's the beginning number that you want to start at? Last is the ending number that you want to start at. So if I wanted to create an array from 1 to 20, right? And how the numbers are spaced in between, that depends on what's called the increment. So for example, if I wanted to go from 1 to 20 in steps of 2, so it would be 1, 3, 5, 7, all the way up to 19. So it wouldn't actually be 20 because it goes out. So you'd actually get an array from 1 to 19. And you control that by step size. It tells you how much you need to add the previous number by to produce the next number. So for example, if I wanted to create an array from 0 to 1.1 in steps of 0.1, you do 0, 0.1, and then 1. Right, so 0, colon, 0.1, and then 1 or 1.1 or whatever. Okay. If you forget to include the increment, that's totally fine. It just means that the increment is assumed to be 1. So for example, if I wanted to create an array from 1 to 20 in steps of 1, you'll have 1, 2, 3, 4, 5, 6, all the way up to 20. You just do 1 colon 20, and that's it. Right? I kid you not, that's exactly what you do. So here are some examples. If I wanted to create an array from 0 to 10 in steps of 2, you do 0 colon 10 colon 0 colon 2 colon 10. Okay, so what this will do is that it creates a 6-element array where you do 0, 2, 4, 6, 8, and 10. So it goes from 0 to 10 in steps of 2. If I wanted to create an array from 3 to 30 with increments of 3, this would mean 3, 6, 9, 12, all the way up to 30. If I wanted to create an array from 1 to 2.2 in steps of 0.1, you'd have 1, 1.1, 1.2, all the way up to 2.2 in steps of 0.1. So the increment tells you how much you need to add the previous element by to get the current element that you want. You can also go backwards. You can also start from a number and then you can decrease by an increment of a negative kind. So for example, if you wanted to create an array from 3 down to -3 in steps of -1, this would be 3, 2, 1, 0, all the way down to -3. And then last but not least, if I wanted to create an array from 5 to 15 in steps of 1, you'll do 5, 6, 7, 8, right? You can either code this manually, or you can do the 5 colon 15. So you start from 5, you end at 15, and this is assumed to be in steps of 1. Okay? You can also perform this using what's called the linspace command. Right? What the linspace command does is that there are 2 ways that you can call the linspace command. The first way is this, where you specify the beginning, which is the first, the beginning number that you want to see, which is first, and then the ending where you want to stop, which is last. So first and last are pretty much the same construct as what you've seen in the previous slide. And then you can also specify the total number of points that you want. So what linspace does is that it starts from the first number, goes to the last number, and then it equally divides the range between n equally spaced points. Okay? So for example, if I wanted to create 100 points between 0 and 2, you would do 0, 2, and then 100. If you forget the n operator, if you forget the n parameter, that's totally fine. What this means is that you're just assuming that n is equal to 100, and it'll just create 100 equally divided points for you. Okay? So for nonlinear equations, you can try using the log space. Right? Log space, what that does is that it will logarithmically give you, it'll logarithmically space points between the first number and the last number. So this is exactly the same style as linspace, but you have a logarithmic scale instead. So what's going to happen is the difference between the first few numbers will be big, and then the difference will become smaller and smaller as you proceed to the end of the array. So this pretty much is sort of like what we've seen earlier. Okay, so let's move on to some more advanced functions for plotting. So for example, if I wanted to create this function handler, it's very simple. You do 5 times sine x, minus x. We did this already. You create that function handler, and let's generate our set of x points. So what we're going to do is we're going to create an array from minus 5 to 5 sets of 0.01. So you're going to get minus 5, minus 4.99, minus 4.98, all the way up to 5. Okay, and then you're going to run through a function that we're going to take this, and you're going to apply it to this function handler, which means that it's going to take this equation and move and apply it to every single one of these points, and then it'll give you an output that applies that function to every single point for the corresponding location. We use an increment of 0.01. The reason why is because when you run the plot command, the default behavior is that it draws all the points on the graph and it just connects a line through them. So you'll notice that if you make this increment larger, there won't be that many points, and the distance between each corresponding point is going to be large, so it's going to look a lot more jaggedy, and that's not the kind of plot that you want. So the smaller the step size that you get, the more accurate the plot's going to look like, so this is what we're going to get. Okay, and that's very nice. So, it plots a graph, this is from minus 5 to 5, and then this is the y value. Still a very basic graph, but we'll get onto how to modify the look of this later. If you wanted to plot more than one graph on the same window, like if you wanted to show more than one trace, like if you wanted to put 4 graphs on a single plot window or 5 graphs on a single plot window, you would use the plot command by putting pairs of x and y points together. And each pair will make a new trace on the window that you have. Okay, so for example, each pair of arrays will generate a plot in a different color. So MATLAB has its own way of coloring graphs. So for each pairs of points that you have, it'll draw a new graph that's of a different color for you. So you're going to specify pairs of points. So you have x and y, so these correspond together, right? You have these correspond together, and so on and so forth. You have to make sure that pairs of points have the same length, or it's not going to work. Okay, so if you use the previous example, this is going to be minus 5 to 5. I made a little mistake here. And then you're going to apply the function handler to this set of values, so you get that. And then what I'm going to do is I'm going to create 2 more new graphs. So what you're going to do is you're going to just simply take the function, just add it by 1. So you're going to shift the graph up by 1, and then you're going to shift the graph up by 2. And then what I'm going to do is I'm going to plot all these together in the same graph. So if you take a look here, the x coordinates, they're the same length as any of these, because all we're doing is we're just using the function handler, we're just adding it by 1. So these are automatically going to be the same length. And then you just do x and y, so this will be the first graph, this is the second graph, this is the third graph, and what you get is this, which is great. So MATLAB has its own color coding system, right? And then you'll see that each graph is added by 1. So this is a very nice graph, but you probably want to know which graph is which. You want to probably give it a title. You probably want to label the axes and so on and so forth, or you probably want to give it a Cartesian grid too. And these are the commands that we're going to specify that will help you do that. So we can customize the graph to make it look a little nice. So to label the x-axis, you use the x-label command. X-label meaning you're going to label the x-axis, and then you're going to specify a pair of round braces. And then inside you're going to specify a title within single quotations that's surrounded by it. So you just replace it with whatever you want. So you can call it, time or frequency or whichever the horizontal axis pertains to your problem. And then you can do the same thing for the y-axis. It's very simple. Just replace, instead of x-label, you use y-label. Same construct. You're going to label the y-axis. And if you want to put a legend, okay, how the legend's going to work is that you have to name the graphs in the same order as how you place them in the plot command. So if you go back to here, alright, so the legend, when you specify the first title in the legend, it's going to correspond to this graph. When you specify the second title, it's going to be this graph, and this is the third title. Okay? So you got to make sure that it's in the same order as how you specified, how you specified in the plot command. And legend just takes in a string of, a string of strings. So you specify single quotes. This is the first title, the second title, and this is the third title of whatever graph you want. To name the plot, use the title command. Very simple. Just use title and then perform, use single quotes and do that. And then if you want to add grid lines, use the grid command. So to be able to add these, nice features, you have to be sure that you create the basic plot first. So you do plot and then, x, y, or whatever. And then when you're done, use these commands with the graph window still being open. You can minimize it, but make sure you don't close it, and then you can run these commands. So you have x label x and then y label y. I'm going to call it the very original title, 3 graphs. Plot a grid on it, and then we will place a legend where the first graph is y equals fx, the second graph is 1 plus fx, and the third graph is y plus 2fx. Okay? And that's what it looks like. Very cool. Grid lines are awesome, and then you have these lines or the graphs where the legend tells you which graph corresponds to what function. So it's not bad. Okay. By default, MATLAB takes each pair of points in the arrays and connects them. It does a connects the dot kind of thing. It also has its own way of coloring each plot. So there's got to be a way for you to control not only the colors of the plots that you want to plot, but the way that the plots are drawn. So do you want to have markers for each point? Do you want to not draw a line through each point? And you can control that by specifying a third additional parameter, which is a string of up to 3 characters that are surrounded by single quotes. So not only will you do x and y, you'll also specify a third parameter where the first character specifies the color that you want the graph to be, right, the line, and then the second and optionally the third parameter the character will specify how the line style or how the plot is going to be drawn. So the supported colors that we have are B for blue, G for green, R for red, C for cyan, and so on and so forth, M for magenta, Y for yellow, and K is for black because blue is already taken with the letter B. And here are the supported styles. So you can specify a dot, you can put a dot as for each point, you can specify a circle for each point, a cross, an addition sign, and so on and so forth. Okay? So here are some examples. If I wanted to plot y is equal to x, from 0 to 10 in steps of 1, you just want to draw a very simple line. Here are some basic options that you can use to plot your graphs. So if you were to do plot and then x comma y comma and then in single quotes you have g dot, this means that you're going to plot a green line with dots at each point, but you're not actually going to connect all the dots. Each point will just be a single green dot. Okay? If I wanted to do, plot x, y, and then bx, what this is doing is that it's similar to what's above, but you're going to make the graph blue, and each point will be represented as an x with no line through each of the points. Same thing, you can do it with black, and then you have it with circles. And then last but not least, this is pretty interesting. You're going to have, it'll be a magenta line. Not only will you have dots, but we're going to connect all the points together. So this will basically be a straight line with dots at each particular point. Okay, like how you saw before, you can do multiple plots. I'm not going to go through this as in a lot of detail, but like what you did before, you can specify triplets of points, triplets of values. So this will be the first graph, and then you can specify whatever line style that you want. This is the second graph, whatever line style that you want, and so on and so forth. So you can go from 1 up to n, where n is the number of plots that you want. So all you got to do is just you specify a pair of triplets. Each triplet you modify according to what line style that you want or what color that you want, and then you can use X, Y label, legend, and grid or whatever as long as you have the plot window open. So when you do this, then you can do those things after. Okay? So let's say we wanted to plot multiple graphs on a separate plot, multiple graphs and separate plots on the same window. What that means is that you'll have a single window, and then you'll have multiple separate graphs. So you'll have like 4 separate windows inside a big window, with each window having a particular plot. And you can use this by what is known as the subplot command. So what the command does is that it treats the figure window or the graph window as having multiple slots, and each slot will take a graph. So how you use this command is very simple. You use the subplot command, and then you do bracket, and then mn and p. What m and n are you have to know beforehand what these are. You have to figure out how many rows and how many columns you want. So how many slots do you want? Do you want 3 slots for do you want 3 rows and 2 columns, which means you have 2 slots? Do you want 3 rows and 3 columns, which means you have 3 slots, and so on and so forth. So you need to know the number of rows and columns you want beforehand. And then p, what p does is that it chooses which slot you want the graph to go to, and then you just go ahead and do your plot. Alright? So how p works is that it's an index, right? So the order is from left to right and top to bottom. So we'll go through this in a little bit more detail later. So in order to use the subplot command, you have to call the function first. After you call subplot, then you can use all the standard plot syntax that you've learned to make that plot for that particular slot. And then when you're finished, you move over to the next slot. So here's a quick example. Let's say I wanted to make a window with 4 plots in it. You have 2 rows and 2 columns, which means that you're going to have 4 plots. So the index is going to go from 1 to 4. So it's going to go left to right and top to bottom. So if you do subplot 2, 2, 1, or 2, 2, 1, what this will do is that it specifies the top left corner. You code the syntax that you need to plot the graph normally, and then the plot will finally appear in the top left corner. All right. If I wanted to make the graph such that it appears at the top right corner, you do subplot 2, 2, 2. It codes that syntax normally. You code the syntax for the plot function normally, and then it'll appear in the top right when you're done. Similarly, if you want to do it in the bottom left corner, you do 2, 2, 3. Run your code, and then 2, 2, 4, and you're done. So with this, let's do another example. Let's say I wanted to make 4 graphs, 2 rows and 2 columns, and each graph is just going to have a single plot by itself. So to let's make each plot. Let's make one plot to be sine, the next one to be cos, and then the other one is 3 times x, and the other one is 6 times x. Okay, so you have 4 different graphs. So let's make the range of the plot from, let's say, from -10 to 10 in steps of 0.1. Okay, now what? So what you're going to do is first you're going to create a blank window, and then you're going to start adding each graph to the corresponding slots using the subplot command. And then you're going to customize each graph first before you move on to the next one by using subplot. So you have -10, 0.01, and then 10. So we're going to create our y values. So we've created this vector from -10 to 10 instead of 0.1. You'll have cosine of x, so you're going to, this would be the first y values, the second y values, and so on and so forth. This creates a blank window, and then when you do subplot 2, 2, 1, you can do 2, 2, 1, or just 2, 2, 1, whatever you want. This will specify the location at the top left. Okay, and then you plot the graph, and then we'll do your x label, your y label. We'll just call it plot 1. If you do subplot 2, 2, 2, this chooses the top right corner, and then you'll specify the plot, and then you'll specify the label. This actually should be small case. I'm sorry about that. You have the x label, y label, and then the second plot there, the title. And then we'll do the same thing for the third. You have the bottom left corner, 2, 2, 3. You plot your stuff, and then 2, 2, 4, the bottom right corner, you plot your stuff. And then what's going to happen is that it's going to look like this. That's great. Not too bad. All right. So this is 1, 2, and then 3 and 4. So the subplot command works by that p number follows left to right, top to bottom. And m and n always stay constant. You got to be sure how many rows and columns you want before you proceed. Okay, so one last thing before we move on to more advanced stuff, for more plotting 3D graphs or whatever, is we can customize which values along the x or y axis we want to display. So what you'll do is when you're plotting a graph, you'll see that the numbers on the x-axis, the numbers on the y-axis are automatically chosen. So if you want to specify specifically, or you want to show exactly what the x values are on the x-axis and the y values are, you use the set command. So you do set bracket and then get current axis, and then the string tells you which property of the figure that you want to modify, which is the x-axis, and then you specify an array of values that you want the x-axis, the x values to appear. So if you wanted to show numbers from 1 to 10 in steps of 2, so 0 to 10 in steps of 2, you would do 0, 2, 10. And it'll show those numbers on the x-axis only. And then you can do the same thing for the y-axis. Instead of x-tick, you do y-tick. So array is the values that we wish to display for either axis stored as an array. So here's a quick example. Let's say from x is from 0. Let's say x is from 0 to 10 in steps of 2, and then we're going to do y is equal to x. When you plot this, what we'll do is we'll manually specify that we want 0, 2, 4, 6, 8, and 10 to appear here. You use the xtick command, and then for the y-axis, I want 0 to 10 in steps of 1 to occur. So 0, 1, 2, 3, up to 10, and you do that. So you can manually specify which values along the x and y-axis you want to show. And then, last but not least, we're going to move on to 3D plots, and then I think here we'll take a little break, and then we'll get on to some advanced MATLAB constructs. For the second part of the tutorial. Okay, so let's move on to 3D plots. MATLAB can draw 3D plots in a very nice way. Here are the basic steps. What you need to do is you have to create a function handler that has two variables with it, x and y, right? And then what you got to do next is you have to figure out the range of x and y values that you want. So you want to graph it between, x is -2 and 2 and y is -2 and 2. Just like the 2D plots where you specify a range of x values, now you got to specify a range of x, y, and z values. So once you're done, you're going to use a function handler to evaluate all these points to give you what the output is for the third dimension, which is z, and then you're going to use a function that plots this triplet of arrays, x, y, and z, in 3D. So how do we generate a grid of x and y values? We're going to use something which is called the mesh grid function. This function outputs two matrices which are called x and y. So what this does is that when you generate these two matrices, what it does is that it shows you the x and y value for that particular location in Cartesian space. So x contains what the x coordinates are in the grid of points that you want, and y contains what the y coordinates are. And I'll show you an example of that in a little bit. So you need to specify the range of values that you want to plot using mesh grid. So there's two different examples. The first way is to do it this way. So x1 and x2 is the beginning and the end value for your x. So if you wanted to go from -2 to 2, this would be -2 and 2. And if you wanted to figure out the range of the y values, you'd do that here. So let's say you wanted to plot a graph between -2 to 2 and 0 to 3 for the y. So you'd have -2, 2, and then 0, 3. Also, if you wanted to specify increments, by default, this is increment of 1. So if you wanted to specify increments of anything other than 1, you can do that in this style here. So this is pretty much what we've seen before. So you have beginning, end with increment, and the same thing for the y, and then you get your output matrices as so. Okay, so x1 and x2 determine the beginning and the ending x values, and y1 and y2 determine the beginning and the end y values. So you can specify increment as we've seen before. So as a quick example, let's try doing a mesh grid where the rows go the x values. In this case, the x values are going to be let's see here. In this case, this x corresponds to vertical coordinates. Right, and then when you're dealing with mesh grid, you got to be careful where the x corresponds to rows and the y corresponds to columns. So x will be the y in this case, and y be the x. So you got to be careful. So this corresponds to the rows, y corresponds to the columns. So we're going to specify a range from 0 to 4 instead of 1, and then the same thing from 0 to 5 for y. So this is what the output's going to look like. All right. So when you do 0 to 4 and then 4 to 5, so here's what the grid looks like. So the top left corner, the x coordinate is 0 and the y coordinate is 0. And the corresponding elements in the x and y will tell you that the x coordinate is 0 and the y coordinate is 0. If I wanted this location here, this is 2, 1. Okay? So, let's see. So right, this is 2, 1. So what'll happen is, oops, oh, sorry, okay, I do have this right. So x is this way, y is, okay, so I'm sorry, forget about that. X is going to show you the horizontal coordinates, y will show you the vertical coordinates. So if you wanted location 2, 1, you go to the corresponding element, which is here, so the x value is 2, the y value is 1. If I wanted to go to this location, right, the x value is 3, for this location, this corresponding location here, and the y value is 3. If I wanted to go here, the x location is 2, the y location is 4. So you're going to the corresponding location, the physical coordinate, the coordinate in Cartesian space, and then you can get the x and y value as so. Okay? So each matching location from both the x and y matrices corresponds to the actual physical location in Cartesian space. So now, how do you create 3D plots? You either use the surf or mesh commands. All right? So surf, what that does is that it produces, the third dimension, the z values, as having all different colors assigned to them. So what it does is that the height of the z values will determine what color it's going to be filled in as, and it's basically a closed plot. What a mesh plot does, think of it as a wire mesh plot, where all you're doing is you're just connecting the lines. You're connecting lines between the points, but you're not coloring in any of the areas that enclose the points. So once you're done, you just specify, for each function, you specify a triplet, the x, y, and z values. They got to be all the same size. And then you can continue and customize the graph using the commands that you've seen previously. So you can use title, you can use a grid, and so on and so forth. So let's do a quick example here before we decide to take a break. Okay, so let's plot the following function. Let's say I want to plot this function in MATLAB using either a surface plot or a mesh plot. So first, you're going to create a function handler which depends on x and y. So you have add x, y, and then x dot star. So remember, you're multiplying, and then any exponentiation operators, you do a dot hat, right? Exponential. And then what we're going to do is we're going to create a set of values. Sorry, between -2 to 2. And sets of 0.2, and the same thing for the y coordinates. So our range is going to be from -2 to 2 and -2 to 2 and sets of 0.2 for the x and y. So we're going to concentrate it on a 4x4 grid between -2 to 2 for x and -2 to 2 for y. Okay, so once you're done, run this command into your function handler, right? And this will give you a set of z points for each corresponding location in Cartesian space. And then once you're done, you're going to run the surf command, which will give you what that plot looks like, and then you can label the x and y and z axes accordingly, and then you can put and then you can do whatever you want. When you run the figure command, it creates a new window, and we're going to do the same thing, but we're going to show you what a mesh plot looks like. And that's what it looks like. Okay, so how it works is here it actually shades in all the the areas that are enclosed by the points, right? So the amplitude will tell you the way that the coloring is organized. And then you can do the same thing for this as well. So red means that it's the maximum point, and blue means that it's the lowest point. So a mesh is pretty much the same thing, but you're not shading in any of the areas. Okay, so we're going to take a little break, and then we'll go through some useful MATLAB commands and constructs or whatever, and then we'll get on to some more advanced functions.